In this video we're going to look at modelling the addition of two numbers using the IEEE 754 standard. Now if you get into the resources section you'll see an Excel spreadsheet there called Add Subtract. So if you go ahead and open that up and make sure you're on the Tools tab. Now on the Tools tab you're going to have these options available to us. Now we're interested in the one that says Add Subtract. Now we won't be able to run this until you've set up your environment correctly within Excel. So I've got Excel 2010 here, so yours might be slightly different depending on your version. But I get into File, Options and Trust Center Settings. Now in my settings here under ActiveX settings, I've got the third one down, which is prompt me before enabling all controls with minimal restrictions. Also for the macro setting here, I've got the bottom one, which is enable all macros. Now you can go ahead and enable all macros, and at the end of using it you can change it back to what it was previously if you require. So that will allow you to run the macros within our spreadsheet. Now there's one other thing that you're going to have to do. If you want access to the actual code, it'll be under the developer section. So we want to make sure you've got this developer tab here. Now in order to get the developer tab, again if you get into File and you get into Options and you can get into Customize Ribbon. Now in this Customize Ribbon you can see here I've got actually a developer tab here and it's ticked. Okay, so if this was unticked, or even it may well even be over here. So you may have to bring it from here over to here and ensure that it's ticked. And this will ensure that you've got this developer tab here. So that will allow you to go in and look at the code in the background. Now I'm no Excel VBA guru, but I have written enough code in order to get things up and running as quickly and smoothly as I possibly can. So if you get into, say for example, the developer tab, and you can type in click on View Code, then you're going to have the code window, and there's quite a lot of stuff in here, but the forms here, click on the forms and you'll have the Add Subtract, and it'll bring up the Add Subtract form and it shows how the form's built. And you can also drop in, if you click on any of the buttons, and it drops into all of the code. So that's all of the code here for this program. Now it's not all complete at the moment. There's stuff that I still have to add, but we'll add those in later on in the course as we add in subnormal numbers and also the rounding and special values. So that gives you enough information, I hope, in order for you to get started. So if you've set everything up properly, you should be able to click on this Add Subtract button and it'll bring up this page here, and it'll take a few seconds to initialize, and then it'll bring up the interface. So this is our Add Subtract interface, and this is going to aid us and help us along our way to understanding the 32-bit floating point addition and subtraction. Now we're going to always start from the bottom and work our way up. We're going to have an X value, we're going to have a Y value. So we're going to put our initial values in these boxes here. So our X will go in here and our Y will go in here. So if we put our value, say 7 in this box and a value 5 in this box, then the 7 is going to be represented by this 32-bit floating point number here. And this is our X value in our 32-bit floating point binary. And the Y value is going to be represented by this 32-bit floating point binary number here. So this in effect is just a conversion from our decimal to our floating point for our X and Y. Now you'll note also on the right hand side we have the hexadecimal version for these numbers. So there's going to be an 8-bit hexadecimal number. So for example, the very last one here is number 4, and it's the last 4 bits here. So it's going to be these 4 bits. So it would start off 1, 2, 4, 8. So that would be the number 4. And again, we're going to have another we're going to have 8 of these altogether representing this number. Now whenever we form the addition, the answer to this obviously is going to be the answer 12. And again, the answer 12 is written up here in our 32-bit floating point representation. And also the answer is also represented in our 8-bit hexadecimal value. You'll note also that we've got the number type written in the left hand side. So 7 and 5 and 12 are all normal numbers. Now that'll be handy whenever we start looking at subnormal numbers. Now, the thing to note here is that we also have our rounding bits, but we don't have any rounding within the code here at the moment. The rounding will be added in later videos. So I suggest that you open this up and have a little play with it and make sure you understand how it is working. Also, we can see that we can subtract the numbers here by pressing the button here. So that will now be 7 minus 5, which is a value of 2. And we can also put in positive and negative values. So for example, we could have minus 7 and we could have minus 5 here. So we would have minus 7 plus minus 5, which is minus 12. Or we could subtract these two off. So we could have minus 7 minus minus 5, which is equivalent to minus 7 plus 5, which is minus 2. So we've got all the options here of adding and subtracting positive and negative numbers. And we can also make our y value greater than our x value. So we could have 7 here and we could have our 5 here. So this allows us to put in all of our 16 possible combinations, which we looked at in the first video, and we should get the correct answer out here. So let's change this back to our 7 plus 5. Now you'll notice in the background here we've got some information, and that information is going to be contained within this tab here, which is the add underscore subtract tab. And this is going to describe exactly how we're going to work through the addition and subtraction over 32-bit floating point numbers. Now we're going to start off with our simple addition, and we'll work through this example of our 7 plus 5. Now what we have here is our y value and our x value, and you can see that we've got our 32 bits. We've got the first bit is the sign, the next 8 bits is the exponent, and then the other 23 bits are the mantissa. Now you won't see all of the bits because I have had to increase the size of the font in order for you just to see what we have here, but we're going to have our 23 bits off the end of the screen here. So we've got a copy of our y value. So for example, our y value here is our 0, 1, and then it's all zeros with a 1. So we've got our 0, 1, all zeros with a 1, and then the mantissa is 0, 1, and then all zeros. So that's 0, 1, and all zeros. So that's just a simple 32-bit copy of our y and a 32-bit copy of our x. Now, we said also that we're going to have to look at the values for the exponent. So if you come down here, we've got a little table. Now we're not interested in all the things in this table for the moment. The first thing we're interested in is the exponent value for x. And you can see here, that's this value here. So this is just a copy of the 8 bits. Sorry, this one here, copy the 8 bits for the x, and a copy of the 8 bits here for the y. Now in this instance here, they're actually exactly the same because the numbers sit within the same exponent range. So that's going to have a decimal value of 129, and that'll have a decimal value of 129. So we're just going to have our 1 plus the 128, which is 129. Now this is the unbiased exponent value. In order to bias it, we take away the 127. So the biased exponent is going to be the small ex and small ey. So we take the 127 away, we've got our 2 and a value of 2. And we're interested in the difference between these two. So the difference is going to be our ex minus ey. So that's going to be 2 minus 2, which is 0. So that's just telling us that there's no difference between these exponents in this instance. Now the other line here we're interested in is the sign. So you can see here we've got our sign for x, which is 0, our sign for y, which is 0, and we've got our sign z. Now our sign z was the exclusive OR of these two, and we've got our final sign for the result, which was our exclusive OR for these two, and also if the number within the absolute value bracket was a negative, then we had to use the little truth table which we've seen in the previous video to get the sign for the result. Now we're not interested in any of this, we'll get onto this whenever we actually start looking at the subtraction. Now each row of this spreadsheet here represents the 32-bit floating point addition and subtraction algorithm, which adheres to the IEEE 754 standard. We start off with the lines 2 and 3, so this is just a copy of our y and x values. So that's our original y value and our original x value. Now we said that we wanted to make sure that the exponent for x is greater than the exponent for or equal to the exponent for y, and we wanted to do that in order to cut down the amount of circuitry we have, and also to ensure that in order to get the final answer we just pick the largest exponent, which in this case will be the exponent for x. So we may well have to swap this y and the x round about in order to ensure that ex is greater than or equal to ey. So let's say for example we had this value here, let's say x was 5 and our y was 5,000. That would mean that the value for our y here is going to be greater than the value for our x. And what we're going to have to do in that case is swap these round about. And you can see here in this instance the swap has taken place between rows 2, 3 and rows 5 and 6. So in this case here the 0, 1 and then the 1, 0, 1, 1 is in the top row here, and you can see the 0, 1 and the 1, 0, 1, 1 is in the bottom row here because we've swapped the both of them round about. In effect the y's become the x and the x has become the y. So within the algorithm now what we want to do is now deal with these two values, and this one here at the top is our y and this one is our x, but we've actually swapped the two numbers around. And you can see here below that our new value for our x is this value above, which originally was our y value, and the new value for our y is this one down below, which originally was our x value. So they've been swapped round about, and I've swapped them here as well. So let's go back to our 7 plus 5 because that's the one we really want to be working with. Now in the instance here with our 7 and our 5, the exponent values are both the same, so we didn't have to do any swapping. So it means that this line 2 is exactly the same as line 5 and line 3 is exactly the same as line 6. They're just copies. Now what we want to do is add in the extra bit. So this is the extended, the mantissa being extended to 24 bits. So this is our hidden bit being added. So we have our original number here for our y, which is going to be 0, 1 and then all zeros. And you can see here that we've got a copy of this here, but it's shifted down to this point. So we've now got 0, 1 and all zeros. And we've done the same for our x value. We had 1, 1 and then all zeros. And again, this has been shifted to this point and we've got 1, 1 and all zeros. Now what we've done is we've added in the hidden bit. And now in the hidden bit for a normalised number is going to be a value of 1. So that's this 1 being added here. And you'll notice I've just put them in red just to show that this here is the hidden bit. So the full stop would be sitting just at the junction between the red and green boxes here. So the full stop in effect would sit at this point here. Now you'll see I've added in an extra bit here. Now this isn't an actual bit that we add into the IEEE 754 standard. This is just a bit I've left in so we can see exactly what happens whenever we add the two numbers together, because whenever we add two numbers together, there's got a potential of one of the bits to be carried into this extra bit here. So this extra column here is not a real column in terms of the IEEE 754. I've just added it in order to make the description a little bit easier, and you'll see that in later videos whenever we start looking at what's in this column. So now what we want to do is we want to shift the mantissa for y. That is, we want to shift it by a value of ex minus ey. Now in this instance here, it's quite simple. Ex and ey are the same. So whenever we take ex minus ey, we get the value of 0. So we're just really saying that both these numbers sit in the same exponent range. That is the range from 4 to 8. So it means that in this instance here, the shift is going to be 0. So all we need to do is just take a copy of our y. So this is the y mantissa here, so we simply copy the y mantissa here, and then we can copy the x mantissa down below. So we'll go through an example next on the next video where we're going to have the y will have to be shifted, but in this instance here we're not having to do any shift. So now what we want to do is add these together. So whenever we add them together, you can see that we can't see all the way off the screen here, but it just goes all in zeros all the way along. So whenever we perform the addition algorithm, we simply add these two rows together. So 0 plus 0 will give us a 0, 1 plus 1 will give us a 0, and we'll carry 1 over, and we'll have our 1 plus 1 again will give us a 0, and we'll carry 1 over, and then we'll have 1 plus 1 plus 1, which will give us a 1, and we'll carry 1 over, and you can see that we're carrying 1 over into this extra column which I've added in here. Now we want to choose the exponent value. Now we want the exponent for x to be greater than or equal to the exponent of y. So we're going to choose the exponent of x. Now in this, for example that we're using, both the exponents are the same and it wouldn't actually matter which one you chose. But for consistency, we'll continue to choose this exponent for x. So we copy this over into the final value here, and this is going to be our exponent value. Now another thing to note here is that we're going to have this one bit here, and this one bit is the carry out of the mantissa. So if we've carried this out from the mantissa, we're going to have to carry it into the exponent. That is, this 1 is going to have to be added on to the exponent value, and it's going to have to ripple all the way through. So in this case here, we're going to add this 1 onto this 1, and we'll get a 0 and we'll carry 1, and then we're going to have no more carries because this is a 0 here anyway. So the new value is going to be 1 more. So the actual value for the exponent is going to end in 1, 0 as opposed to 0, 1. Now you can see here why this is happening. We're going to have two numbers, and these numbers are going to be sitting in the same exponent bin. But whenever we add both of them together, 7 plus 5 is going to get into 12. Now 12 is the next exponent bin up, so this number and this number sit between the values of 4 and 8, but the answer sits between the value of 8 and 16. So we've had to add 1 on to the exponent in order to get it into the correct exponent bin, and that's what this carry out does. It carries out of here and it ripples up through and adds 1 on to the value for the final exponent. So finally we're going to have to normalise the result and get rid of the hidden bit. So in this case here, we can see that the decimal point would be sitting at this point here. So it means that the number to the left of the decimal point is going to be a 1 and also a 1 there. So in decimal, in effect, that's going to be the number 3. So that's 1 plus 2, which is 3. But we can't have the mantissa value any greater than 2. It's not allowed. In order to keep the number normalised, the mantissa value always has to be between a value of 0 and a number just slightly less than 2. So that means that this has to be normalised. So we're going to have to take the decimal point from here, and we're going to have to move the decimal point up to here. So in effect, what we're going to do is we're going to make the mantissa smaller. So in effect, we're going to take the mantissa and make it a smaller number. So rather than a number between 2 and 4, it's going to be a number between 0 and 2. So we've got to shift the decimal point up to here. And then when we shifted the decimal point up to here, this is the normalisation phase here, then we're going to have to get rid of the extra bit. So in this instance here, we get rid of the extra bit, and the final answer here is going to be a value of 1000. So this is the final answer here. Also, the sign bit you can see is going to be given by our SX and our SY, which have been exclusive ORed, and that's given the value of SZ, which is a value of 0. So that's the first addition that we've looked at. Let's quickly have a look at this again mathematically, just so you can understand this normalisation phase properly. So let's say, for example, we take two different numbers, 4.8 and 6.4. When we add them together, we get 11.2. Now both of these numbers sit in the same exponent bin. That is the number between 4 and 8. But whenever we add them together, it's going to go on to the next exponent bin, which is a number between 8 and 16. Now in this example here, that answer is 11.2. Now if I was to write this out in the exponent format, that would be equivalent to 1.2 times 2 to the power of 2. Now work that out yourself. 2 times 2 is 4. 4 times 1.2 gives us the 4.8. Now this other number here would be 1.6 times 2 to the power of 2. So you can see here that the mantissa value is a number which is less than 2. The mantissa value is a number that's less than 2. But whenever we add these together, we're going to get the number 1.2 plus 1.6, which is going to be a number 2.8. Now in this instance here, the exponent value now is a number which is greater than 2. Now we can't have the exponent number as a value of greater than 2. So if you were to check this out, 2.8 times 2 to the 2 would give us the 11.2. But we'd have to ensure this exponent value was a number less than 2. So what we can do is we can increase the exponent here to a value of 3. So this is equivalent to the number rippling up through the exponent value. But whenever we do that, we're going to have to decrease this here by a factor of 2. So that's going to be 1.4 times 2 to the 3. So this is going to be an exponent increase, which is the ripple, and we're going to have the normalisation, which is making the mantissa smaller by a factor of 2. Now we're always going to have to do that if the result here is greater than 2. So mathematically what we can look at is we're taking the result for the mantissa and we're dividing it in this instance here by a factor of 2, and we're taking the exponent value here for the result and we're adding 1 on. So this is the ripple and this here is the normalisation. So we can go ahead and put those values into the calculator here. So we can put in 4.8 and we're going to add in the 6.4. When we add those together we get 11.2. Now notice it's not exactly 11.2. That's because the representations here are not exact values in the 32-bit floating point binary. So if we were to then look at what we have above, you can see that the answer here is going to be, well, the decimal point is actually there. So this is going to be 1, 2, so that's going to be 2, and then we'll have the rest of the mantissa will give us the 0.8, so that's the 2.8. But as I said, that's not normalised. We want the value of the mantissa to be less than the value of 2. So what we have to do is we can ripple through this 1 into the next exponent. So it means the exponent goes up by a factor of 1, a factor of 2, and the value for the mantissa will have to go down by a factor of 2. That is, we're going to have to divide the mantissa. So we divide the mantissa by shifting the decimal point from here to here. So that's the normalisation phase. So it means that the normalised result will be 1.011. And then what we do is we get rid of the hidden bit, which in this case now will be the 1, and we'll just be left with the 011. So that's us left with this 01100. So that's been quite a long video, and I've went through it in quite a lot of detail, but you've learned a lot about how the tool's going to work, and it means the videos from now on will be a little bit shorter. So I suggest you go ahead and you pick numbers for yourself, and maybe just pick numbers where the exponent values are the same, so that you're going to be adding x values that are within the range 0 to 2, 2 to 4, 4 to 8, 8 to 16. So the values, for example, 32 to 64, so you might have 36 plus 42, and you'll see that the answer will get into the next exponent range up. So you can put your own values in, and you can work through this spreadsheet and ensure you understand exactly how each of the lines operate in order to give you the answer, and ensure you get the answer that you expect. Also remember that we've got the other tools here for doing the conversions if you want to stick the conversions in yourself. Okay, so this will work through to generate the numbers. So you can go ahead and use these tools here as well. That's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.